So this is the title. I would like to thank the organizer for the invitation. And the objective of this talk, okay, the subject of this talk is I took inspiration by the title averaging. And to me, maybe averaging does not mean the same thing as means to people from dynamical system. So I will consider simple, I think simpler situation, okay? But maybe the idea can be extended to more complicated situation like dynamical systems, okay? And so there will be noise, and there will be some regularization in the sense that we will have some PDE, and we add noise to this PDE, and then things behave better, okay? So you put bad thing, and things behave better, okay? It's not very usual. And the other keyword is pathwise, okay? Essentially, I will not use probability anywhere, okay? Okay, so I'm probabilist, which does not, which like not to use probability very often. And okay, so this is, okay, so the point is that, so the punchline is that you put something bad in your system and things behave better. Okay, and you try just to find out example where this happens. Okay, many times what happens is that you put something bad and things get worse. And here, if you pay attention to some detail, maybe in some cases things behave better. Okay, because essentially what the noise is going to do, we will use probability just to mimic some generic situation. Okay, so you want to point out today, okay, you have a PDE, but this PDE has some problem, but if you think about real situation, maybe the coefficients of the PDE are not so regular, they may be very wiggly in space, so actually you want a more generic situation, and you mimic it adding noise to this equation, okay? And the point is, okay, so now we want to use some noise, but we want not to talk about probability, okay, or at least very few probability, okay, because probability has its own problems. Okay, it's easy to use expectation, but then, like yesterday in the talk with Kiefer, if you want almost sure result, then you have to pay more attention. Okay, so if you think, if you will, we will try to have almost sure results in a probabilistic setting. Okay? And so the kind of example I will show you are the kind of, so I will start from ODEs because it's easier. And we will add additive noise to this ODEs and see that things get better. And then we slowly try to look at some more complicated PDEs. Okay, and so transport equation and even nonlinear, some kind of nonlinear PDEs. Okay, and since if I will show you that the theory is not void, so I will give you a notion of irregularity and show you that the theory is not void in the sense that if Brownian motion has this kind of irregularity, fractional Brownian motion has this kind of irregularity, and it will be interesting to see if, for example, dynamical systems are source of this kind of irregularity. Okay, this is open problem to me. And I should mention also that all this is joint work with Remy Catellier and Khalil Chouk. So Remy now is in Rennes and Khalil in Berlin. So let's start from the simplest situation, just to have, so this is more or less review of the stochastic results, okay, you have. So what we know from the point of view of SDs is that if you take SD perturbed by additive noise, okay, like this, and then so from the point of view of solution, it's trivial. You can even solve in space of continuous function. You don't need stochastic calculus to solve this kind of integral equation. And if B is Lipschitz, okay, you have solution. Now, the point is that even the people have found that even if B is not Lipschitz, this kind of equation has a unique solution in various sense, okay? And there are many results starting, essentially, these are in some sense all the results by Veretennikov, but then Davy has made very nice and key computation on this problem. And then there were some work about Krylov and Rochner, Flandoli, which were finer and finer in topologies, and what kind of condition on B you have to impose. And essentially, the condition on B are some kind of integrability condition, okay, in order to ensure uniqueness of solution. So uniqueness is a very strong notion of uniqueness. Essentially, it means that, so in many of these work, but not in Davy, essentially in many of these work, it means that given Brownian motion, there is only a continuous adapted process to the Brownian motion that solves this equation, okay? Even if, essentially, if B is L infinity, okay? So this is very strong notion of uniqueness. And then in Davy, there is an even stronger notion of uniqueness, which means that given a Brownian almost surely, given a Brownian path, these almost surely depend on B, but okay, you fix B, then you find a full set of Brownian paths for which this equation has a unique solution in the space of continuous function, okay? It does not even to be measurable process, okay? Just you give a Brownian path, and then there is only one continuous function x of t which can solve this equation for B bounded, okay? Think about this. So you see here, there is no probability at all, okay? You choose, there is an exceptional set of paths, but you remove it at the beginning, and then everything else is an analytic statement, okay? And then you can do this starting from ODEs, then you think, okay, ODEs are linked with this very simple PD, which is transport equation with, okay, the noise just produce some kind of multiplicative noise in the PD, in the stochastic PD. And then there were, starting from work of Flandoli, myself, and Priola, there were results about L infinity solutions for this equation. Okay, so you make a weak theory for this equation. You're looking for function U, which are L infinity, which solve this equation.
If provided you interpret the right-hand side as a Stochanovich integral.
Yeah.
It's the Stochanovich correction is hidden. We make it a second-order equation.
No, it's not true, because you don't have regularization. Okay, you know it better than me. You don't have regularization in this equation. Okay, you point out correctly that this has to be Stratonovich in order to have links. If you don't have Stratonovich, you have some different equation. But for Stratonovich, it's really transport equation, in the sense that the initial condition is transported along the flow. So you don't have any regularization of, these are pathwise results, okay? So you, in the later, so at the beginning we have different proof using the flow for this equation, and then later in this last work we made a full PD proof which use the Laplacian, which use the generator, but is a bit tricky, okay? It's not so easy. Of course, the average, so what Etienne was pointing out is that the average of U solve a parabolic PD, okay? But if you want pathwise result, it's not so simple, okay? Because this is not parabolic PD, okay? The solution does not get better as time goes on. If you start from if you start from initial condition, which is just L infinity, which has a jump, this jump is propagated along these characteristics, okay? So the solution does not get better with time. And so this has to be understood in a weak sense. You don't have choice. And there are counterexamples showing that if B is not Lipschitz and you don't have this term, you don't have uniqueness in the PD. Okay, so this is the point is that if you add the noise term things, you have uniqueness for this PD in L infinity. If you don't have the noise term, you can build a counterexample which you show that there is no uniqueness. Okay, so things get better at the level of uniqueness. And then there are other results. And also, okay, I will not spend time at this level on this. Okay, you can, you see, you are adding, essentially, in all these equations, you are adding noise, but at the highest level, okay? Noise cannot be understood of a perturbation of a lower order term. Okay, it has to be the highest order term in the equation, in some sense, okay? In order to provide some effect. Otherwise, it's just a perturbation and things cannot get better. And there are works about modulated Schrödinger equation, I will show you later, that is where you put, essentially what you put is, you put a random sign in front of the Laplacian of this Schrödinger equation, okay? And this random sign changes very fast, so converges to white noise, and then you can understand this equation very well, actually it's not so difficult, and you have some kind of regularization effect. From the fact that instead of having just a fixed sign in front of the Laplacian, you have something moving, okay? So I will show you, so I will try to, so the point of, so maybe it's too ambitious, okay, but I will try to show you that you can essentially discuss in a given setting all these kind of equation, okay? This is the transport equation. So you add some so you see now you get out of the stochastic setting, okay? I'm not thinking anymore to Brownian motion. I give myself a continuous function W, taking values in RD, and try to make sense of all these PDEs, okay? Where here you put the derivative of W, okay? And think about Brownian motion, so you don't want to assume that W is differentiable, okay? Because I want to be able at the end to put there Brownian motion, or sample path of Brownian motion. And I have something which holds almost surely. Okay? So you have various problems. The first problem is how you understand the PDEs. And the second problem is how you use this term to make the theory of the PDE better. Okay, you see this is the modulated equation I told you before. This is just Schrödinger, nonlinear Schrödinger equation. So this is a model of propagation of impulse in the waveguides. And since the waveguide, so the time direction is the direction along the waveguide, okay? And the space direction in these models is the direction transverse to the waveguide, okay? And since the photon has nonlinear effects inside the waveguide, you have nonlinear term. And the fact that the waveguide is very long and maybe non-homogeneous, actually engineers built inside, so what they found is that if they put in homogeneity in the waveguide, the impulse is preserved better, okay? So this was found by engineers. It's called, they modulate, okay? It's more modulated fibers. A modulated fiber propagates signal better than homogeneous fibers, okay? So you want to understand this mathematically, so you put some kind of noise there, okay? Which is not homogeneous. And there are people that, okay, when you start to believe that this kind of thing happens in dispersive equation, then you also would like to see what happens in other model of dispersive motions. And another nonlinear dispersive equation very well known is Cordova-de Vries equation. Okay, so you try to do the same here. So all these equations are not very difficult to understand, okay, in some sense, because you can reformulate it as a mild equation. And so, for example, I will show you in the case, let me take an even simpler problem, okay? You take a given function and you try to solve this linear transport equation, okay? So there are no vector field, given vector field, there is only this perturbation. So you're essentially taking a container and moving around the container, okay? This is what you are doing. And you can write the solution explicitly, okay? If W is smooth, then you have a very precise relation between these two, but you see this formulation makes sense for any W, okay? This is just like the perturbation of constant formula, okay? The Duhamel formulation for this equation. So these are, so in the smooth setting, solution can be represented in this way. And so you see that the key object in the analysis of this equation is this averaging operator, what we call averaging operator, okay? And so you take, so what is doing this operator is taking a function and then averaging this function along the trajectory of a given continuous function, okay? And so this will be one key object for us, okay? So, okay, since you are not doing nothing, okay, because if F is regular and W is regular, you don't think that this is going very far from having the same property as that one. And, but actually something interesting happens, okay? This is a very interesting problem to see what are the properties of F which get improved by this operation, okay? So let me go on. And simple case, so I will not go through this computation, okay? But simple case, in dimension 1, so this now depends on the dimension, okay? In dimension 1, you can take the perturbation and being very smooth, like the identity, and you still have some effect, okay? Because you see, you reason just 5 minutes and maybe 2 minutes, and then you realize that even if F is just bounded, the averaging of F is Lipschitz. Okay? It does not have any time regularity. Or you have two kind of estimate. Okay? Either you have this Lipschitz estimate or you have this Lipschitz estimate in space or in time. Okay? Essentially, the averaging operator allows you to trade the space, the time regularity of the integral for the space regularity of the function. Okay? So you can have the two. So if you interpolate, you can have anything in between these two estimates. Okay? So averaging gets better in one dimension. Okay? But this is also only one dimension. Okay? In more than one dimension, you cannot use a smooth function to regularize. Okay? Because smooth functions single out a direction, and you will have a averaging effect in this direction, but not in the transverse directions. Okay? Now, there is a very, I cannot understand this paper, okay? But there is a paper of Tao and Wright, which is very long, which essentially means, okay, I can give you a suggestive view on this paper, that W is a smooth function, but it has to have non-trivial geometry, okay? It cannot stay on a plane, it cannot stay on a line, it has to wiggle around in all the space, okay? So think about a function in RD, which does not conserve any plane, or, okay? So it has to wiggle around, but it's smooth, okay? And the point that after 40 pages of very incomprehensible computation, they show that you have a regularization effect, okay? But this is about integrability, okay? It takes a function of some integrability, so f is in LQ, it takes it to some function in higher integrability. Be small, I think they cannot really quantify this precisely, okay? But they show that it's higher, okay? But the relation to the wiggling, it's complicated. And the proof has some kind of dynamical mini-infinity, okay? You have to understand how bolts are transformed along the motion of this W function, okay? So maybe somebody of you is interested to looking at it and to understand what's going on. And Davy, so this is the computation, the very interesting computation that Davy has done. Alexander Davy is in Edinburgh. So he found out the following, okay? That you take Brownian motion now you take a function f, and for any function, you can find a full set of Brownian paths for which the averaging operator is Lipschitz in space with some regularity in time, order in time, okay? So this is better than this, okay? Here you have either Lipschitz in space or, okay, if you want to have 1/2 order in time, you are bound to have 1/2 also of regularity in space by interpolation between these two, okay? But here is better, you have 1 and 1/2, okay? So essentially, you gain, this is, well, okay, this 1/2 is not very important here, but you get, and is not related to the Brownian motion, okay? You can have other processes like fractional Brownian motion, you always have 1/2 here, okay? It's some kind of central limit theorem, but not about Brownian motion. It is about the fact that it's Gaussian, more important. But this is related to the fact that it's Brownian motion, okay? And you see, you take a bounded function and it becomes Lipschitz, okay? So the idea is that what is happening to the vector field in the ODE case is that even if the vector field is bounded, it is effectively some kind of Lipschitz function for which uniqueness can be applied, okay? This result is pathwise, okay? You give me the function f, and I find a full set of Brownian paths for which this holds everywhere in space, okay? But of course, the weak point for this result is that it depends on the function f, okay? It's not a property only of the Brownian path. It's the property of the Brownian path and the function f. If you give me a different function, the exceptional set is different, okay? So I cannot say something for all functions at once, okay? And I will be interested really to understand what happens as this averaging operator as an operator, so as something for which, something all for any function. So let's go on. So in order to try to understand the behavior of this operator more consistently, you try to introduce other function spaces, okay, to see its mapping properties, okay? So if you, for example, think about Sobolev spaces of functions, so now you think about F being in some Sobolev space. Now you realize that the Sobolev norm of the image can be understood as, sorry, this is L2, okay, it's not Sobolev. As the L2 norm of the Fourier transform, okay, of this Fourier transform, okay? This essentially, the averaging operator acts some kind of convolution operator. So in Fourier space, it's just multiplication for a given function, and this given function is given by this integral, okay? It's the integral of this phase factor. This is fun. If you think about putting Brownian motion, it's a random function, okay, but it's a function. And now you can also introduce, now these spaces, for some reason, I like them more, even if they are more difficult to understand. These are some kind of, you are trying to measure the L1 norm of the Fourier transform instead of the L2 norm. So in this setting, is the kind of space which work a bit better, but they are not easy to understand, okay? If you give me a function, it's not easy to say if it lives in these spaces. The only thing I know is that, no, I think it's the reverse. I always get it wrong, okay? Exercise for you, get it right, okay? I think if it live in this, it's the reverse, okay? If it live in this space, it's an older function. Yeah, yes, okay? If it live in this space, then it's an older function, okay? Because you can make a computation for the increments. So it's the other way around, okay? Now, so this is definition that we make in our first paper with Remy, which is here. So you can ask detail to him. Is the following. We said, okay, now you give yourself a function, you make a definition of a space of function. Okay, I say a function is irregular if this very strange object goes to 0 uniformly as psi goes to infinity. So rho has to be positive quantity. So if this Fourier transform goes to 0 as psi goes to infinity, and so smallness where, so this is the increment of this function, okay? So when t and s become together, it has to be quite small, and uniformly has still to go to 0 as psi goes to infinity. And if you give me a function which has this property, I call this function irregular, okay? This is give you a space of function, okay? You can test if you give yourself a function, you can test if this holds uniformly or not, okay? Define a norm on these functions. And, okay, so this is our first definition. This is the key point. So the key message I want to sell you today without any price, so it's free to take you home, is that in all the example I know of averaging, if you are ready to pay a bit, because of course these are almost sure results, okay? So if you want to go to average result to almost sure, you always have to pay something somewhere, okay? Because you will have Borel-Cantelli somewhere which needs to pay something, okay? So if you have space to pay something, usually in averaging, then you can have almost sure result only knowing this property, okay? All the example I showed you before can be handled only knowing this property of the path. So if you give me an irregular path, whatever it is, it's fractional Brownian motion, it's Brownian motion, is some kind of homogenized path from a dynamical system, whatever, but if you are able to prove this estimate, so gamma has to be bigger than 1/2 in the key estimate, in the key application, okay? So if gamma is just a bit bigger than 1/2 and rho is whatever, this path has some regularizing effect, which get better as rho get higher. Okay, so the regularization power of your path is encoded by rho, given that gamma is a bit bigger than 1/2. Okay, so think about. So this estimate is not very easy. Okay, if you give yourself up, even with a deterministic path, I don't know, is an oscillating integral. It's very tricky to estimate. Okay, so it's not very easy. And they are full of problems about this irregularity, notion of irregularity. I will show you later how to use it, okay? But let us see what's going on. Let us see what we can say about this irregularity. So if you have fractional Brownian motion, which is generalization Brownian motion. I will not enter into detail, but essentially Brownian motion corresponds to this parameter being 1/2. Then you can prove that almost surely any paths of fractional Brownian motion are irregular for any rho less than 1/2h. Okay, so if h is 1/2, this is 1. Okay, rho, yes, less than. So regularization power for Brownian motion is almost 1. If you can take, in fractional Brownian motion, the interesting thing is that you can take h going to 0. Okay, you still have a process, well-defined process, and then you see that there are paths, there are random process for which the regularization effect is arbitrarily high. And the fractional Brownian motion has this property that if you give yourself any function, smooth, whatever, you can find the probability that the fractional Brownian motion lie in a ball is positive. Okay, so you can always find a path of a fractional Brownian motion arbitrarily near any given function. Okay, this is maybe the probability to find it is very small, but at least there is one. Okay, if probability is positive. So you will have a path, you can have a path with arbitrary high regularization effect near any given profile, okay, by this probabilistic construction. Other very interesting this I find very amusing, very funny, is that if a function is irregular, it cannot be too regular. Okay, so I call that notion irregularity, okay, but you can ask why it's called irregularity. And now, it's called irregularity because you can prove this, okay, because it cannot be too regular. Okay, so you have a lower bound, upper bound on the Holder exponent of the function, okay? If the function is irregular and is Holder, then the Holder exponent cannot be too high, okay? And you have a bound like this, okay? The more rho is high, the less the exponent has to be big. Okay, because this is not possible that you have this condition. Okay, and the proof, okay, I will not go the proof, but the proof is essentially this line. Okay, it's not very difficult. You use some kind of Young integral. I will show you later. Okay, just to give you, motivate you a bit. And apart from that, I don't know any reliable way to prove that a function is irregular. Okay, and there are plenty of open problems around. Smooth function, if dimension is bigger than 1, a smooth function cannot be regular, okay? Cannot be regular at all. Because you see, you require that this Fourier transform goes to 0 uniformly on A, and what you have essentially, you understand that it can go to 0 in the direction of the derivative of the function W, but not in the transverse directions, okay? So it cannot be uniformly going to 0, this Fourier transform. You need a function which near every point go in every direction, okay? So you really need some irregular function, like Brownian motion, okay? So you have something like this, but you want this kind of uniform bound in any direction, so you cannot have this. Now, if you perturb, so even, and now even simpler situation, like take Brownian motion that you perturb by a infinity function, I would like to say that it has the same regularizing power of Brownian motion. Okay, locally looks like Brownian motion. I'm not able to say this. Okay, the most what I can say is that you lose if you perturb. The only estimate I have come from an argument, a deterministic argument like this. And if you perturb an irregular path, you lose essentially half of the regularizing power, okay? But intuitively, this is wrong, okay? So this proof is not the optimal one, okay? And using a probabilistic argument, you can prove that your intuition is right, okay? If, for example, you take fractional Brownian motion, you take an adapted smooth perturbation, by using probabilistic technique, you can prove that it's actually very easy because this process has the same, has a law which is equivalent to the law of the original process, W, okay? So an almost sure result is the same for the two, okay? So if W is rho irregular, the W plus phi has to be rho irregular, okay? Probabilistically. But you have to use probability to show this. I cannot show it analytically, just using the notion of irregularity. I have to use the law of this process, the full law of the process. So there are many things to understand, okay? And you find all we know, essentially, in Catellier thesis. And there are relation with intersection local time. And you have irregularity for stable Levy processes, and a relation with the non-determinist and many other results. No, okay. In the thesis, only this, but okay. You can cook up other results which are not still written down. Okay, but just to tell you, there are a lot of open problems. If you want to pick them up, I'm quite happy. Okay? I cannot solve them. I'm not able to solve them. So what then, putting everything together, you can prove that if the path is irregular, then you have this regularization effect in the scale of Sobolev spaces. You see, it's some function which in Fourier space goes to 0, okay? So it helps you, in Fourier space, the operator acts as a multiplication, so improve the property of the function. And you gain, in the regularity, you gain rho, essentially your regularization, okay? In the Sobolev space, and think about Brownian motion. If you want to get lost, for Brownian motion, rho is 1, almost 1 minus epsilon, okay? So you can take an L2 function and it becomes almost H1, or you take these Fourier-Lebesgue spaces and you gain still 1. Okay? The open problem is that apart from these spaces which are characterized from Fourier transform, we don't understand very well the mapping properties of this operator, okay, with respect to irregular functions. So these are pathwise results, okay? They depend only on the notion of irregular function. Then you prove apart, then, for example, sample paths are irregular, but these are pathwise results. Very easy. Okay? I'm not selling you hard computation. I'm selling you a notion, okay, which seems to be used. We were surprised because at the end it came out to be useful in many contexts. Okay, so they are not the computation that are very complicated. Okay, things start to get complicated when you want to put inside a older function. Then this I don't know. Okay, I don't know the mapping properties of this operator in the range of older spaces. Okay, it's more tricky. For anything which is not related to Fourier transform, is more tricky. Okay, even if you can use wavelet, it's still tricky. So I don't have much time. Let's say 10 minutes, maybe a bit more because I started a bit late. So let me go on smoothly. And we start to, so I show you before that if you don't put this term, but you put a source term, then this averaging operator is relevant to the problem, okay? And now we look at this transport equation, okay? You have a vector field B, and you have your perturbation. Now, what you know from the deterministic theory, essentially, is if B is not Lipschitz, this equation has not uniqueness, okay? B has to be, you can allow a bit less, okay? You can allow BW11 or B, the vector field B, BV. These are boundary cases, but essentially, if it's just order continuous, then you can show that you cannot have uniqueness, okay? And the point is that now I want to add this term and show that you have unique solution. And in the Lipschitz case, you have uniqueness, and the only solution is given by the method of characteristic. Okay, you flow according to the flow of this differential equation. Okay, and the uniqueness of the solution is related to the uniqueness of the flow for this equation and the smoothness of the flow. Okay, if you have a Lipschitz flow for the equation, then you can use this information to have a uniqueness statement for this equation. Okay, the two are essentially the same. So let's see how can I use W to show that this equation has unique solution and very nice flow. Okay, that's the point. Okay, you have to do a computation where you see this effect. Okay, because it's not evident how it applies. And so the computation, maybe it hints you that the averaging operator is important, is the following. Okay, you have to freeze, essentially, you see X is the composition of two things, the path and this Lipschitz function of T. Okay, think about B bounded. So this is a function, Lipschitz function of T, and you have a path. So X is the composition of the two. So you think about perturbing by freezing this part, but letting this go. Okay, in this ever. And so you write, you write theta as X minus W, and you rewrite this equation in function of theta, which looks like this. Okay? This is just a change of variable. But then here you freeze this term. You try to freeze down to make a perturbation argument. This is like in David Kelly, I think, talk. Okay, you have to, it's like you have a fast and a slow variable. Okay, you have to think as W as the fast variable and theta as the slow variable. Okay, you try to make a perturbation in this sense. So you try to write the dynamics of the slow variable in terms of only something which depends on the fast variable, but you freeze the slow variable. Okay, this sense is averaging. And you see that the averaging operator came up very naturally. Okay? If you freeze the slow variable, then you have the averaging along the trajectory of the fast variable. And this integral, so in this integral, you have to understand that the averaging operator depends on time and on space. Okay? So here you differentiate with respect to time, and then you apply the function theta s, which depends on space. But I don't want, and so you write this kind of integral in this form, okay? You understand that's the limit of the Riemann sums, okay? At each step, you make, it's like some kind of splitting method, okay? You make a step for the fast variable, and then you update the slow variable, and then you go on like this, okay? To separate the two scales. And you define this integral can be understood as the limit of the Riemann sums. And you can prove that you don't need that g to be differentiable in the time variable to make sense of this integral, okay? Because essentially, if the slow variable has a slow dynamics, you have some kind of average going on, okay? So I don't want to enter to the detail, but you have some kind of Young integral going on, which is just the easy way of do a rough part, okay? Now, this is just rewriting, okay? But the point is that this form of rewriting allows you to use the theory of Young integration, which says that whenever you integrate two things, and you have an integrand and an integrator, you can balance the regularity of the two. Okay? If your integrand is smoother than what you think, you can use this smoothness and require less from the integrator. Okay, so you have a trade-off. So here I want to use theta. You know already theta is Lipschitz. Okay, so you know theta is very good.
It's not a product.
No, okay, this is some kind of nonlinear Young integral, okay, but the proofs are not very different, okay, it's not linear. Actually, in the work of David Kelly and Jan Melbourne, you can show that if you make an abstract functional construction, you can understand it as a linear operator, but in some more general space, okay, you have to understand the application of the theta has to be understood as the composition with the delta function in theta, and then it linearizes the problem, okay? But actually, if I didn't want to write this in that way, and we didn't want to do it in that way, you can just look at the proof and see that it goes on in that case, okay? It's not much difficult. But it's a nonlinear composition, okay? G is a function of x, general, and you put inside some function of time, okay? So it's a nonlinear Young integral, but nothing very exciting, okay? You don't have a very difficult. You have to adapt the spaces and things get out naturally. But the point is that this equation now, in some sense, G in this equation, the vector field is Lipschitz, okay? Because it's the averaging of B, and I show you that you can gain regularity. So you can put up condition in which B is not Lipschitz, but the G, for the kind of estimate you need, it's a Lipschitz function. Okay? And then you have uniqueness and existence and whatever you want. I want to skip because I think this is much related to maybe something that Devi said about this fast loss system. So you have a result about existence, uniqueness, and smooth. You have to have the good conditions, okay? But essentially, you can have even smooth flow if B is a bit more regular. Okay? And think about putting really, you can have rho as high as you want, okay? If you put inside the fractional Brownian motion very irregular, okay? So you can even start from a vector field which is bounded and end up with some G in this equation which has 20 derivatives, okay? So your flow will have 20 derivatives, okay? That's is as simple as that, okay? More or less. And okay, then you have a good theory for this equation. Okay? You can have even more. Okay? That's why the reason we introduced this kind of Fourier-Lebesgue spaces. Okay? You can have distributions as B. Okay? Because alpha, you see, at the end of the averaging, alpha gets improved by rho. A rho can be 10. Okay? So alpha can be -5. What does it mean? It means you can put delta function, for example, inside your equation. Okay? And still have pathwise meaning for solution, pathwise meaning for this quantity. This quantity can be understood. So you see, this integral, when you put a distribution here, you cannot understand analytically anymore. Okay? With bounded function, it still has a meaning as Lebesgue integral, but if you put a delta function here, for example, as a distribution, you cannot understand analytically. But this Young integral featuring this averaging operator makes sense for B as a distribution in some cases. Okay? And the meaning is quite natural. I don't know if I write it. Okay, this is not bad. Okay, the meaning, let me write on the blackboard the meaning because, so what is the meaning? The idea is the following. Okay, you want to define this object. Let's say, take a simpler situation. Take just the unperturbed case. You have the fast variable. You want just to define this when B is a distribution. Okay, what is the meaning? The estimates, the kind of reasoning I showed you before is that you can define this as some limit. You take some regularization of B, converging in the right topology, then this makes sense. And what tells you the theory, essentially, it tells you that this limit exists. Okay, and then you can give it a name and call it this integral here. Okay, so you have a very natural notion of integration for irregular paths, along irregular paths. Okay. Now maybe I will spend the last. Can I have 5 minutes? Yeah. I spend the last 5 minutes to explain a bit what. So this was about the ODE. So my title was PDE. So what you can do for PDE. For PDE, you have an interesting intersection, okay? Because you want to have a meaning for the PDE, where here you put an irregular path, okay? But then, of course, I show you that an irregular path is not regular, okay? So this cannot have a meaning as traditional PDE. And I show you, and this is pathwise theory, so I don't want to use Ito integral or Stratonovich integral, okay? So you have to come up with a meaning, intrinsic meaning for this equation if you want to have a theory where you can say it has unique solutions. Okay? And I don't want to use the flow either, okay? Because I want to have a uniqueness statement, so I want the largest class of function I want. So I want just to say that I have some distribution U, which solves this equation in some weak sense, and this distribution has to a uniqueness for this equation. Okay, this is recent work of Remy, which studied this problem. For this linear transport equation. And so you see, you have the regularization, you have the irregularity. So regularization is the good part, and the irregularity is the bad part, give you problem, because I cannot give a meaning to this equation. So in order to give a meaning to this equation, you have to use the theory of rough path, okay? In the sense that think about weak formulation for this equation, but weak in space. So you test with functions which depend only on space, okay? And then this equation means that the function ut, so the function u at time t tested against the test function phi of space, has to satisfy this equation here. Where now here is well-defined object. Here you have a problem because you have to define what does it mean this integral, okay? But this integral can be understood as a rough integral, okay? Using the theory of control rough path. Okay? So you can formulate the PDE at the level of rough path or rough integrals as saying, okay, I'm given an object U which satisfies this for any T and S. Is it unique or not? Okay, can I have uniqueness or not for this object? And if you don't put this, is a standard weak formulation for the PDE. And if you put this, you have to use this rough path to give a meaning just to this integral. But then you show, so okay, what is the meaning of this integral? It's you can give a meaning, okay, to the integral. We will not enter into this detail, okay. But what you can show essentially is that is that if using the flow, essentially a posterior, you can use the flow to construct a good test function for this problem, and using the flow you can prove uniqueness, okay, for these equations. And yeah, okay. So this for me was very nice because you have two different theories which has nothing to do one of the other. Okay, you have this averaging theory and rough path, and in this example you have to put them together. Otherwise, rough path give you a problem, and the averaging solve this problem by giving uniqueness. Okay, existence is trivial in the. Oh, okay, it's trivial. Is not very complicated, okay, for proving that at least one solution of this PDE exists. So the problem is how to prove uniqueness. Okay? And you use the flow which constructed before for the characteristic to prove uniqueness for this PDE. Then I think I will stop. Okay, these are just something about the equation. I will not enter into this second part of the talk but just to mention that it was curious for us, but the same object, this irregularity, this notion of irregularity appears also for these two equations. Okay, you can use this notion of irregularity to show that this equation has a pathwise, some kind of pathwise regularization phenomenon going on. Okay. And the point is that if you write the mild formulation for this equation, they are essentially like some kind of variation of constant. You have to you remove the nonlinear term, you solve the linear problem, you call U of W the solution map for the linear problem, then you have the Duhamel formula for the nonlinear problem. Okay, and you see that this formulation is valid for any W, okay? Because in this formulation you just have the group generated by the linear part computed at the time Wt. Okay, it's just a change of time for the linear problem. And if you go in Fourier variable, you see that the notion of regularity I show you for W, give you some very interesting estimate of the nonlinear term. And with this estimate you can cook up solution theory for these equations. Okay? And this is very important because this equation, in some sense, if you put this perturbation, you break the analytic method that functional analysts were using for this equation. Okay, so you cannot anymore use the standard method. Okay, there are methods related to Bourgain spaces, which work in Fourier transform in time. And so if you have this kind of non-homogeneous perturbation of time, you cannot take any more Fourier transform in time, okay? Or at least it's not obvious how to take it. So I think I will stop here. Okay, thank you very much.
Thank you. Any questions or comments? Yeah. Just wait a second, we have a microphone.
Do you have a notion of irregularity based on wavelets instead of Fourier space?
You can, okay? You can write it down. So this is related to the problem of the older spaces. Actually, we have problem to understand the mapping property of this operator in any base of space. Okay? The point is that you cannot find useful estimates for the averaging operator applied to wavelet basis or Littlewood-Pelly basis. Okay, but this is from the problem. So from the analysis, you can write it down something reasonable. Then at some point, you have some probabilistic object, which is the averaging operator applied to a wavelet basis, and you have to come up with the right estimate for this object. Okay, so this is the problem. It's an open conjecture. If you look at our paper with Rémy Catellier, there is a conjecture. The point of this conjecture about the behavior of this averaging, and the point of this conjecture is that if you can solve this conjecture, more or less, you can have a mapping property for wavelets, spaces based on wavelets, so all the Bezos spaces and all the Tribel-Lizorkin spaces.
This wavelet description would also connect more natural with Martin Heire's notion of roughness. Is that right?
No, why you say so?
Martin had
so
this notion of...
This is truly rough.
Exactly.
No, I think Khalil Chouk has taught a bit. It's not evident how to relate. So everything about, so you have to understand that this object is very, from the point of view of analysis, is very tricky to estimate, okay? So I told you, even if I put a smooth perturbation, I break up any reasonable estimate. So it's not easy to understand what does it say about the pathwise property. Probably something truly rough. I think, but Khalil should have some result about this. Something truly rough has to be, maybe something irregular has to be truly rough. But I'm not sure, it's very difficult to understand this. But of course, this is what you expect. But it's not related to wavelet, okay? This is just a way to analyze the function W, okay? Can just take this Fourier transform. And truly rough and this notion of roughness has to be related. And then the point with the wavelets, the problem with the wavelets is that the wavelets are localized in space. And we do not understand very well the behavior of the averaging for localized functions.
Thank you.
Any other questions or comments? So if not, then let's thank Massimiliano again for the talk.
Thank you.